Hello, today we're going to take a look at 3.5, which is higher derivatives. So all rules of derivatives follow through each level of the derivative. But what we're going to learn today is that you can take the second, the third, the fourth, etc. derivatives, and some derivatives have direct application and some not something that we're going to study. So find the derivative of y equals 3x to the fourth plus 2x. Then find the derivative of the result. That's the instructions for our warm-up. So we're using y prime for our notation, power rule, 12x cubed plus 2. Now if we want to derive this result, right, the result is going to be 36x squared. So we started with a fourth power polynomial, it went to a third, and now it went down to a second. So derivatives higher than the second derivative sometimes exist as well. The third derivative will be the derivative of the second derivative. The fourth derivative will be the derivative of the third derivative, and so forth. So we can see polynomial type terms have very much a pattern here, and they go on for a finite amount of times though, right? So if it's an x to the fifth, the sixth derivative brings us to 0. And then we would just be repeating and we would be getting 0. But there's other functions out there, such as negative exponents or rational exponents, for example, that if we repeated the power rule over and over and over, it would continue to go further negative. So it would not have a finite number of derivatives. It actually goes on forever. There's also other examples out there which we'll start to see where you'll establish a pattern, and then you could repeat this pattern. So for the notation here, we have f, then we have f prime, f double prime, f triple prime. So we can see the first three derivatives, we use those tick marks. After that, we notate the fourth, fifth, sixth, etc. with a superscript of the number itself, 4, 5, 6. It's not that common that we'll be taking that high of a derivative. Typically, if a problem is asking for some ridiculous high derivative, it's because there's a pattern that you can establish. So calculate the third derivative of f at -1 for the given function. So before we can input -1, we need to find the third derivative as a function. So there's no magical step to get from the original to the third. You have to derive in order. So we would have 15x to the fourth minus 4x minus 14x to the -3rd is our first derivative. Our second derivative is 60x cubed minus 4 plus 42x to the -4th. And our third derivative is 180x squared. The minus 4 goes to 0, minus 168x to the -5th. So there's our third derivative as a function, and the problem is asking for the third derivative at -1. So 180, -1 squared, minus 168, -1 to the -5th. Okay, so this would be a positive 180. -1 to the -5th would remain a -1. Multiplied by the -168 would go positive 168. Final answer of 348. Now we're going to take a look at a derivative, or a function, where if we take the first three derivatives, first of all we have a product rule here, as well as an exponential rule. Okay. So we should always start by writing down the rules that we need. Product rule is f prime g plus fg prime. And the derivative of e to the x, remember, just stays e to the x. So those are the two rules that we're going to see. So in this problem, x is our f, e to x is our g. So the first derivative, x prime, would give us a 1. E to the x would stay. Plus, x would stay. E to the x derives, but stays just e to the x. Right, so this gives us e to the x plus x e to the x. Okay. Now, yes, you can factor e to the x out, and some people look to do that and think that maybe that's a little bit easier. But what I want to bring your attention to, right, we still have to derive it 2 more times. But if you notice, the second term is exactly what we started with. So that's where our pattern comes into play. We already know the entire product rule derivative of x e to the x. So when we do our second derivative, we really just have to derive that first term, e to the x, and copy down the derivative of x e to the x. So let me highlight that. That's a little bit confusing. Right? If the original function is in our first derivative, when we derive for our second derivative, then this whole thing will be copied down, right? Because when we derive the green highlight, the result is the red highlight. We've already proven that in step 1. Of course, you don't have to acknowledge this pattern. You can continue to derive repeatedly without acknowledging the pattern. But our second derivative, right, I'll write it out instead of deriving right away, would be the derivative of the first term, independent, there's no product rule there, plus the derivative of the second term, independent, but there is a product rule. And this is the one that I'm saying is exactly what we started with. So e to the x derives and remains e to the x. X times e to the x derives and becomes e to the x plus x e to the x. So I can combine like terms here, and I have 2 e to the x's plus x e to the x. So what you might be noticing now, the first derivative had 1 additional e to the x plus the original function. The second derivative now has 2 e to the x's plus the original function. So the third derivative will indeed have 3 e to the x's plus x e to the x's, but we'll see why. So again, we would derive this first term, independent, no product rule, and the second term, with the product rule. Again, it's a repeat of the original function. So I derive 2e to the x, which is 2e to the x. I derive x e to the x, which is e to the x plus x e to the x. And I combine my like terms. 3 e to the x plus x e to the x. So this is the type of an example where I could say, all right, what's the 100th derivative, right? And you could come up with the answer based on this pattern. Go ahead and try these out. Pause the video, try to get both of these results in, and then start the video back up and I'll show you the results. So you should get 17,904 for your final result of the second one, and the first one should come out to be 24x to the negative fifth. Oh, this is the same problem. Don't need that. Okay, so a real-world application here. Yesterday we said that the derivative of position was velocity. What will the derivative of velocity be? Right, that higher derivative, that second derivative. Acceleration due to gravity. So find the acceleration a of t of a ball tossed vertically in the air from ground level with an initial velocity of 12 meters per second. So, right, if we derived position, our result was a velocity function, which was always that initial velocity minus gt. So if we derive that again, what are we left with? Right, a constant, which goes away, and then that minus gt term. So we're left with gravity. We're left with just negative 9.8. So let's just discover this here, and we can come up with our conclusion. So s of t, the position function, we have to come up with. So it's starting at ground level, which means my initial position is 0. It has an initial velocity of 12 meters per second, so plus 12t minus 1/2, I'm in meters, so 9.8 t squared. Right, so I'm in meters first as a position. I derive it once, rate of change in position over change in time. S prime is v, so it goes to 12 minus 9.8 t meters per second. Right, I derive it again with respect to time. So S double prime, which goes to V single prime, which we are naming acceleration, goes to negative 9.8, and the units are going to be meters per second squared. So let's take a look at these graphs. The original graph here is an x cubed. Right? We can see two turning points. It's a positive x cubed, so end behavior. Left side of the graph is down, right side of the graph is up. The first derivative, right? We know how to derive this. We would get the exact function. It would be a 3x squared plus 4x minus 4, etc. So let's write that down. Right? And then the second derivative, well, that would be a 6x plus 4. Okay, so if we look at the comparisons, right, we can see that in the first graph, right, we are increasing from negative infinity until negative 2. We are also increasing from a little less than 1 here to positive infinity. Those increasing then become positive y values on the graph of the first derivative, whereas the decreasing, which is that middle section, are the negative y values on the derivative graph, and the zeros, or the turning points, the turning points of the original become the zeros of the first derivative. Right? It's all about slope. So if an original function is increasing, the slope of the tangent line is positive. So the first derivative graph is the slope of the original. If the original function is a turning point, the tangent line is horizontal, therefore the slope is 0. Therefore on the first derivative graph we have our zeros, etc. Now, we can do the same exact transition from first derivative to second derivative. And in the future, we'll talk about more about what it means, but for now, I just want to kind of brush on it. So, same idea. Where are we increasing? I'm going to try to change colors so that we don't completely mess up. So we are increasing from this turning point down here, which occurs at roughly negative 1, I'll say. we're increasing that whole right side of the parabola, which means we are positive over here. That turning point that occurred a little larger than -1 is right here, 0, and it was decreasing on the left side of the graph, and therefore negative below that turning point. Okay, so a little bit more on this. The graph of the original function is displayed on the left. Identify curves 1 and 2 on the right as the first and the second derivatives. So original, and then f prime and f double prime are over there. So they have one tangent sketched on graph A, and that shows to the left of, we can call this C. To the left of C is decreasing with negative values. Okay? It looks to be that at C we would have a tangent that is a 0 slope, a turning point, and to the right of C we are increasing. Okay? So those things that I said, decreasing to the left of C, increasing to the right of C, would then equate to or translate to negative on the left of C, positive on the right of C, and 0 at C, which means that graph number 2 has to be the first derivative. And then if we were to do the same idea to go from 2 to 1 to confirm that that other one is the second derivative, right? The pink curve is increasing always and doesn't have any true turning points, which is why the green curve is always positive and doesn't touch or cross the x-axis. So let's look again. So I want you to match the original graph in column A to its derivative in column B, and then to its second derivative in column C. So pause the camera, see if you can figure this out, or pause the video, I'm sorry, see if you can figure this out, and then take a look when I do the matching. So I'm looking at things like, where am I increasing? Where am I 0? And where am I decreasing, of course? So I'm increasing on the far left and on the far right. I have 2 zeros. So I can't be the first graph in column B. I have to be the second graph. The zeros are really the most telling part. I am positive here and here, so that works. Okay, so if I continued with this, right, now I have one turning point. I am increasing on the right and decreasing on the left. So one turning point, 1, 0, positive on the right, negative on the left of it. Okay. Now if I look at my second graph in column A, I have 1, 2, 3 turning points. Increasing, increasing. So positive, positive, 1, 2, 3. Okay. 1, 2 turning points, 1, 2 zeros, right? Increasing in the middle of those turning points. Sorry, I know it's getting messy. Positive in the middle of those turning points. Decreasing, decreasing on the extremes, negative, negative. So everything checked out here. Okay, that's the end of section 3.5.